Today, we're looking at section 2.5, and section 2.5 is about measures of position. So, we have already encountered one value in a data set that occupies a definite position in the set. Which one? Can you think of which data value we know occupies a particular position, is always in a particular place in the data set? And that data value is the median. So let's recall our definition of the median. The median is the physical center of the data set. There are an equal number of entries on either side of the median. So the median is the data value that's right in the middle, as long as we've arranged our data set in order from least to greatest. So the median, though, is not the only positional data value that we have. There are many others that we'll talk about. We'll start with the quartiles. Quartiles are values that break the data set into 4 equal parts. So how many quartiles do you think there are? It turns out there's 3 quartiles. A lot of people hear the word quartile and they think there should be 4 because quart means 4. And quart does mean 4. But what these 3 quartiles do is they break the set into 4 pieces. So the quartiles actually refer to the segments of the data that are created by these quartile values. You can think of it like a loaf of bread. If we had a loaf of bread and we wanted to cut it in 4 equal pieces, the first thing you would do is cut it in half. That's what the median is. The median cuts that data set in half. And then you would take your 2 halves of bread and you would cut those in half. So that's what Q1 and Q3 do. They cut the halves in half. You could actually think of them as medians of the subsets created by the original median. So the 4 subsets are of equal size, but they're not quite 1/4 of the data set. Q2, of course, is the median, and Q2 splits the data into equally sized subsets. Q1 and Q3 are the medians of those subsets, so you can think of them as sub-medians. So let's look at an example. Find the quartiles for this data set. We have 22, 23, 24, 24, 27, 27, 27, 28, 29, 30, 31, 33, 37, 42, 45, 48, 49, 55, and 61. So for our solution, the first thing I'm going to do is find the median. To do that, I'm going to line these data values up in order from least to greatest, and I always like to create one line because it helps me visualize the median better. So here's my data all in a row. Now because there were 19 data values, if I divide 19 by 2, I get 9.5. I'm not really interested in the 0.5 part. I just care about the 9. So I'm going to look at the 9 data values on the left and the 9 data values on the right. And when I underline those, or not underline them, but when I highlight them, you'll see that the value 30 in the middle is left unhighlighted. And that's because 30 is the median. So that's my median Q2. So now you'll see what that's done is it's taken the entire data set and it's made 2 chunks of data to the left and the right. You have the lower set and the upper set. If you find the median of each of those subsets of data, those are going to be your quartiles, Q1 and Q3. So if we look at that data set again, and I look at the 9 data values on the left, there's 4 and 4. So the median of the first set is 27. But it's not just any 27, it's the first 27. So that's my Q1. And then I look at the 9 data values on the right and the data value in the middle. is this 45, and that's my Q3. So my quartile values are Q1 equals 27, Q2 equals 30, and Q3 equals 45. So the rules we learned to find the median of a data set also apply to other quartiles. What rules am I referring to? Well, if there's an even number of data entries in either data subset, then use the average of the two central entries to find that quartile. So just like in finding the median, if there's an odd number, we get to pick the number in the middle. If it's an even number, we have to find an average. Same thing applies to the quartile. Let's look at another example. Find the quartiles for the following data set. So this time we have 31, 37, 42, 46, 50, 51, 57, 63, 65, 70, 73, 73, and 79. So what we have here is 13 data values. So because 13 is an odd number, we'll be able to find one central entry. That central entry is 57, and that's my Q2. This, however, creates subsets to either side of 6 data entries. Because 6 is an even number, when we go to find Q1 and Q3, we'll have to take the average of the two central entries. So on the left, those two central entries are 42 and 46. On the right, they're 70 and 73. So to do Q1, we take the 42 plus 46 and get 88. We divide it by 2, and 44 is our first quartile. For the third quartile, we take the 70 plus 73 and get 143. Divide that by 2, and we get 71.5. So now we have our first and third quartiles. So Q1 is 44, Q2 is 57, Q3 is 71.5. If we look at it on the data set, 57 is there, and we'll put some lines in here to show where Q1 and Q3 are. So you can still see that the quartiles have broken the data into equal-sized sets. We have a set of 3 units here, 3 data units here, 3 data units here, 3 data units here. So once you can find the quartiles for a given data set, we get a new definition. That definition is the definition of the interquartile range. So the interquartile range is the difference between the third and first quartiles. So it's Q3 minus Q1. Remember in 2.4, when we found the range of the data was the max minus the min. That told us the spread of the data from beginning to end. What this interquartile range does is it finds the spread of the data in the middle, right, between Q1 and Q3. How much space falls in that region. What's good about knowing that space is it now gives us a formal way to define the concept of the outlier. We've kind of been waving our hands at outliers all through this course so far, but now we get a hard and fast definition of what it takes for a data value to be an outlier. By using this distance, remember we said it was a data value that was far away from the other data values, that was separated, but we never said how far. The interquartile range allows us to say how far. So what is an outlier? It's any data value that falls more than 1.5 IQRs to the left of Q1 or to the right of Q3. So for example, find the quartiles in IQR for this data set. Identify any outliers. So we have 57, 61, 68, 75, 77, 80, 81, 83, 84, 84, 85, 85, 97, 103, 106. So we have 15 data values here. To identify the outliers, I have to first find the quartiles and define the IQR. So we'll take our data set here and find the median. In a data set with 15 data entries, there will be a central value. We don't have to find an average. So the central value here is 83. That leaves 7 data values to the left and 7 data values to the right. Once we've found our Q2 value, then we can go ahead and find our first quartile and our third quartile. In a subset of data here with 7 entries, we look for the middle entry, which in the first subset is 75, and in the second subset it's 85. So those are my Q1 and Q3 values. So now we've identified the quartiles. Q1 is 75, Q2 is 83, and Q3 is 85. Now we can find the IQR. The IQR is Q3 minus Q1. Q3 is 85, Q1 is 75, so that's 85 minus 75, and 85 minus 75 is 10. So the IQR here is 10. To use that to find outliers, we need 1.5 of the IQR. So we take 1.5 and multiply it by 10. 1.5 times 10 is 15. So 15 is our measuring stick. What this process says is that if you're more than 1.5 IQRs away from the middle chunk of data between Q1 and Q3, then you're an outlier. So the outliers are any data value that's less than 75 minus 15. 75 is Q1, and we go 15 spaces to the left of Q1, and that gives us 60. So any data value less than 60 would be an outlier. And then on the other side, we take our Q3 value and we add 15 to go to the right of Q3. And 85 plus 15 is 100. So any data value that's over 100 is considered to be an outlier. So if we compare this against our data, the outliers are 57, 103, and 106. Those 3 data values were outliers because they fell more than 1.5 IQRs outside of the interquartile range. So how about a practice problem? Find the quartiles and IQR for this data set. Identify any outliers. So your data set is 26, 41, 49, 52, 52, 53, 55, 57, 58, 58, 59, 60, 61, 69, 70, 93, 94, and 99. So you're going to find the quartiles, identify the IQR, and figure out if there are any outliers. So that'll take a few minutes. So while you're doing that, press pause on the video, and when you're ready to see what the answer looks like, press play. Okay, so let's look at the solution. We're going to find our median first. In this data set, we had an even number of data entries. There were 18 entries. So to find our median, Q2, we need to look for the 2 central entries and find their average. The average of 58 and 58 is 58. So my median is 58. But what you need to notice here is that it's not the 58 to the left or the 58 to the right. It's a 58 that exists between those. So that means that the 58 on the left is part of the subset to the left, and the 58 on the right is part of the subset on the right. So we'll shade those back in because they're still part of those data sets, which means that to the left of our median, there are 9 data entries, and to the right, there are 9 data entries. A lot of people will make the mistake and think that once you find that median, that those 2 58s are out. but they're not, because it's not one of the 58s that's the median, it's a 58 that exists between those. So that leaves 9 data values to the left, 9 data values to the right. So I can find the medians of those sets, 52 and 69. And you'll notice we have these 4 data element chunks that are created by these quartiles. So now we've got Q1 is 52, Q2 is 58, and Q3 is 69. Once we have those values, we can compute the IQR and then find the outliers. So the IQR is Q3 minus Q1, which is 69 minus 52, which is 17. So now that we know that the IQR is 17, we need 1.5 of those. So 1.5 IQRs is 1.5 times 17, which is 25.5. So we're going to take this 1.5 IQRs and subtract it from Q1. So Q1 was 52. 52 minus 25.5 is 26.5. And then we're going to take this 1.5 IQRs and add it to Q3. So 69 plus 25.5 is 94.5. So any data value that's less than 26.5 is an outlier. Any data value that's more than 94.5 is an outlier. So the data values here that are outliers are 26 and 99. So if you notice in our data set, we had this 26 and the outlier boundary was 26.5. So 26 was just barely an outlier because it was just barely outside of the distance that we defined to make it an outlier. And if you look on the other side of the data set, one of our data entries was 94. Now the cutoff was 94.5. So 94 was not an outlier, but it was just barely not an outlier, because had it been more than half a unit to the right of that, it would have been. So these distances are hard and fast. We don't get to say, oh, well, that 26 is only half a unit past, so we won't call it an outlier. It is a hard break. It's either on one side of the wall or it's on the other side. It's either an outlier or it's not. There's no fuzziness in that process. Okay. So there's another graphical display that we want to talk about, and it expresses the IQR as well as other data values from the set. It's called the Box and Whisker plot. Okay? And the Box and Whisker plot represents the 5-number summary of the data. So what's a Box and Whisker plot? A Box and Whisker plot is a graphical display of the 5 positional data entries from a data set. The minimum, Q1, Q2, Q3, and the maximum. Those 5 numbers are called the 5-number summary. So what you're going to do is you draw a measured number line. That's important. It has to be measured, extending from the minimum value to the maximum value. And then you plot the 5 positional data entries on that number line. Once you've done that, you're going to draw vertical lines through the quartiles Q1, Q2, and Q3 and create a box around the central half of the data. So it should look something like this. Now, I don't have any graduations on my number line, but in the number lines that you create, you will have the little tick marks for every value between the minimum and the maximum. So let's do an example. Create a Box and Whisker plot for this data set. We have 11 data values. So we've got 27, 31, 34, 35, 36, 39, 40, and 40, 42, 49, 53. So the first thing we need to do is find the quartiles. So to do that, since we have 11 data entries, the median is the 39, and that splits it into 5 data entries on each side. And we can see 34 and 42 are Q1 and Q3. So we've got our quartiles. Once we get the quartiles, Now we can go ahead and draw our box and whisker plot. We're going to need a number line that extends from 27 to 53. So our minimum is 27, our maximum is 53, Q1 is 34, Q2 is 39, and Q3 is 42. Let's create our box and whisker plot. So we've got our number line that starts at 27. Then we've got 28, 29, 30, 31, 32, 33, 34 is in the right place, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53. Why is it important that we have a graduated number line? And the reason is we call this graph a box and whisker plot. The reason we call it that is because it looks like a box that has whiskers. But those whiskers actually tell us something. The length of those whiskers tell us something. It tells us about the shape of a distribution. So box and whisker plots can tell you about the shape of a distribution. If you have a long whisker on one side and a short whisker on the other, then that tells you it's going to be a skewed distribution in the direction of the longer whisker. So here's a practice problem for you. Create a box and whisker plot for this data. So we've got 35, 36, 47, 54, 56, 57, 59, 61, 62, 65, 71, 74, 77, 79, 80, 82, 84. So to create a box and whisker plot, it's going to take you a little while. So press pause on the video, and when you're ready to see the answer, press play. All right, so let's look at the solution. First thing we have to do is find the quartiles. If I do that, my Q2 value is 62. Then to find Q1 and Q3, we have to take averages because there would be 8 data entries to each side of the median. So that's an even number, and we would have to take the average of the two in the middle. The two in the middle of the left-hand data set are 54 and 56. The two in the middle of the right-hand data set are 77 and 79. So we get a Q1 of 55 and a Q3 of 78, along with our Q2 of 62. Now we can draw our box and whisker plot. So we need a number line that stretches from 35 to 84. So our plot looks like this. We've got 35, 55, 62, 78, and 84 all labeled on our number line. We draw vertical lines through the quartiles, which are Q1, Q2, and Q3, 55, 62, and 78. We connect those to make a box. And you can see we have a very long whisker on the left and a very short whisker on the right. So if we think back to our discussion of skewed left and skewed right distributions, if we were to graph this, this has a long tail on the left and a short little stubby tail on the right. So this would be a skewed left distribution. It would have a tail that extends out to the left. That's one of the things that the box and whisker plot can tell us. So quartiles are not the only positional data entries that we know. There are other ones called fractiles. Quartiles are just one of the fractiles. So what fractiles are is they're positional data values that partition the set into segments of equal size. There are several different types of fractiles. We'll start with the quartiles that we've already talked about. Then there's also deciles and percentiles. You may have heard the word percentile before. That one is frequently used. Quartiles give us 4 equal parts, and we use Q1, Q2, and Q3 to define those 4 equal parts. In deciles, deci means 10, so deciles have 10 equal parts. And if you were cutting a loaf of bread to get 10 equal pieces, you would actually make 9 cuts. So there are 9 decile values: D1, D2, D3, D4, D5, D6, D7, D8, and D9. With percentiles, percent means per 100, so percentiles will have 100 equal parts, and to make 100 equal parts, you need 99 cuts. So the percentile values are 1 through 99. Where do we encounter these values? Well, percentiles are commonly used in standardized testing. So whenever you take the SAT tests, or maybe you took in high school the KC exam or SAT-9 test, or some kind of a test that gauged your knowledge, if you took those kinds of tests, then they judged you based on a percentile. So let's talk about percentiles, because people have a misconception about what percentiles really mean. Here's an example. After taking a standardized test, a student's score was reported to be in the 87th percentile. What does that mean? Well, a lot of people think that means they got 87% on the test. It doesn't mean that at all. It means that 87% of all students taking the exam scored lower than the student in question. It doesn't mean that the student scored 87% on the exam. So, to get 87% of the people scoring below them, maybe they only had to score 60% overall on the exam, and it was a hard exam, and 87% of the people who took the exam did worse than that. Or maybe it was a very easy test, and this person scored 96% on the exam, but that meant they were in the 87th percentile because so many people did well. So it's not a measurement of how well you did on the test. It's a measurement of how well you did in comparison to all the other people who took the test. So here's a note. We have some equivalencies with our different fractiles. Q1 is the same as P25. So the first quartile is the 25th percentile. Q2 is the same as D5, which is the same as P50. So the second quartile is equal to the 5th decile, which is equal to the 50th percentile. And Q3 is equal to P75. So the third quartile is the 75th percentile. This actually comes up in your homework, where you're asked to find the 75th percentile for a particular problem. And students will always ask, we never learned how to find it. But we did learn how to find the quartiles. And so if you're trying to find the 75th percentile, just use the process that we learned to find the third quartile, because the third quartile is the 75th percentile. So always look for equivalencies like that that will allow you to do something you haven't done by doing something you have. So the next concept, last concept actually, that we'll talk about in this particular chapter is the z-score. What is the z-score? Well, it's a standardized value that converts each data entry into the number of standard deviations that the data entry lays from the mean. What does that mean? Well, we have this z-score formula. Z equals x minus mu over sigma. That's for a population. And for a sample, z equals x minus x bar over s. What x minus mu is, remember, it's our deviation. It's our deviation of the data. And sigma and s are standard deviations. So we're saying we take our deviation and divide it by the standard deviation. And that tells us how many standard deviations away from the mean a particular data entry is. It gives us a measuring stick. And that measuring stick is the standard deviation. So a negative value for z means that the data value was below the mean. A positive value for z means that the x value was above the mean. And if you have z equal to 0, then that means that the data value is equal to the mean. Now, what you can use these z-scores for is to compare values on differing scales. So the z-score can be used to tell which data values are unusual. Remember this graph that we got when we were studying the empirical rule. Any data value within 2 standard deviations was considered a normal typical value. Any data value from 2 to 3 standard deviations away was unusual, and anything beyond 3 standard deviations was highly unusual and suspicious. So what a z-score does is it converts a data value into the number of standard deviations it is away from the mean. And that will tell us whether it's a usual typical data value, an unusual data value, or a highly unusual data value. Let's look at that process. So here's an example. You take tests in your stats class and history class on the same day. The stats class had an average score of 142 with a standard deviation of 16. The history class had an average score of 76 with a standard deviation of 8. Your score on the stats exam was 178. Your score on the history exam was a 90. In which class did you score best relative to the mean? So we're not asking where you had the higher percent. We're asking in which class did you do better compared to the average for the class. So let's take a look. We're going to find some z-scores. We'll start with the stats class. In the stats class, your score was 178, the average score was 142, and the standard deviation was 16. We apply our z-score formula, which is z equals x minus mu over sigma. We insert those values where they belong. The x is 178, the mu is 142, and the sigma is 16. 178 minus 42 is 36. So this is 36 over 16, and 36 over 16 is 2.25. So your z-score in the stats class was 2.25. What about history? In the history class, your score was 90, the average was 76, and the standard deviation was 8. So we insert these into the z-score formula. Z equals x minus mu over sigma. So that makes it 90 minus 76 over 8. 90 minus 76 is 14, so we get 14 over 8. And 14 over 8 is 1.75. So in both classes, you scored above the mean. But in the stats class, you scored farther above the mean. And as a matter of fact, because your z-score was between 2 and 3, your score was considered to be unusually high. That's a good thing. So you did better in the stats class. So what this allowed us to do was to compare two different scores that had two different scales by comparing their z-scores, which standardizes everything. That's what a standardized test means, is that everything is set to one particular standard, so they're easy to compare. So that brings us to an end of section 2.5. Please look on Pearson for your homework, and have a great day.